Hey, this is Dr. B, and let's talk about limiting and excess reactants. I'm going to show you the method that most people use to solve these problems. Let's call this the normal method. We're burning butane. We know that it combines with oxygen, it makes carbon dioxide and water, and the question is, if I burn 100 grams of butane and I have 100 grams of oxygen, how many grams of carbon dioxide will it make? Well, the thing you recognize about this is number one, it's a gram-to-gram problem. That's a three-step problem. It also gives the amounts of each, therefore it's a limiting reactant problem. We have to find out which one will run out of first. The tried and true method is to take that 100 grams of butane and calculate how much CO2 it will make, assuming plenty of oxygen, and then do the reverse. Take your 100 grams of oxygen, see how much that's capable of making. The lower number will be the answer, since that will be the one that you've run out of, and at that point you're done. It's 2 3-steppers, takes some time. So set it up. There's what you're starting with. You know it's a 3-step conversion. You know you're going to, and you should include that too, blank grams of CO2. You can use a template, or you can just memorize how to do these conversions. It's always from top left to bottom right. 58 grams of butane is a mole. We've converted to moles, but every mole of butane will make 4 times as many moles of carbon dioxide. That mole of carbon dioxide weighs 44 grams. Notice we're going from grams of butane to grams of carbon dioxide. Everything looks good. All the units cancel nicely. It's enough to make 303 grams of carbon dioxide. But will we run out of oxygen first? Let's do the same setup. 100 grams of oxygen, well, 32 grams is a mole, but every mole of oxygen makes fewer moles of carbon dioxide. In fact, 13 only gives you 8. Carbon dioxide still weighs 44 grams, as it always does. And this shows us that we will run out of oxygen after making only 85 grams of carbon dioxide. That is our answer. Time saver. Wouldn't it be nice to only have to do one of these rather than the other? The way I do it is I just imagine the molar masses as written and see if one is enough for the other. In other words, I see that 116 grams of this requires 13 times 32. I don't know what that is. That's like 400 grams or so. So 116 requires more. So 100 requires more oxygen. We're going to need more oxygen than we do butane. We don't have it. It's the limiting reactant. Or to put it another way, time saver. 160 grams, 16 grams, 2 times 58 requires 13 times 32. We don't have that. Oxygen's the limiting reactant. Skip this whole step. Take some courage to do that. Most students just do it by the brute force method. In the next slide, we'll show you an even faster way to do it. So the limiting reactant we've just figured out is oxygen. The excess reactant must be the butane. And then sometimes people want to know how much butane do you have that has no oxygen to react with. The key here is to figure out how much butane will react. The rest must be excess. And let's see, we know that we are starting with 100 grams of oxygen. Let's see how much butane it consumes. There we are. 3-step grams of oxygen, 2 grams of butane. So 32 grams of oxygen is a mole, but every mole of oxygen requires less than 1/6 of butane. Every 13 of moles of oxygen requires 2 moles of butane, so they're equivalent. A mole of butane weighs 58 grams. This shows us that we will burn about 28 grams of butane, leaving us with about 72 grams of butane that are unreacted. This is limiting and excess reactants using the normal method, including how much of the excess remains.